In the previous lecture, we have introduced the Fourier transforms of some spatial signals. One such signal that we have seen was a constant. As I've mentioned in the previous module, that a signal to have a Fourier transform did not satisfy the Dirichlet conditions. So the Dirichlet conditions are the conditions that guarantees the existence of Fourier transform. However, there are some signals that do not satisfy the Dirichlet conditions but still have the Fourier transform, and one such signal that we have seen was the constant signal. A constant signal is not absolutely integrable, but still its Fourier transform exists. We are going to see one more such signal in this module. So next signal that we are going to see is the unit step signal. A standard signal, that is a unit step signal, and you know what is the unit step signal. We have already seen that a unit step signal looks something like this. It is 0 for negative t, it is 1 for positive value of t, and it is undefined at t equals to 0. So I'm going to write that as 0 as a function of t, and this signal is called as u of t, or the unit step signal. The value of this is 1 for positive values of t, and it is 0 for negative values of t. So u of t is defined as being equals to 1 for t greater than 0 and equals to 0 for t less than 0. Now let's try to calculate the Fourier transform of this unit step signal, and I wish to do that by using the Fourier transforms of the signals that we have already seen. Now the aim here is to calculate the Fourier transform, so I'll indicate that with the notation f of u of t, and we need to find this. What is the Fourier transform of u of t? Now let's try to apply some properties, because the properties will help us out in deriving this Fourier transform of this unit step function. Now we have already seen that the Fourier transform of an impulse, so an impulse Fourier transform, so I'll write that as f of del t is actually 1. It's unity. We have already seen that in the previous lecture. And this del of t, we know that del of t, that is the unit impulse, is simply the derivative of u of t. We know that this del t is actually the derivative of u of t. Now as we know that this is the derivative, this del of t is the derivative of u of t, we may now apply the property, we may try to apply the property of the derivative of a function in time domain. As we know from the property that so that's the time differentiation property, from time differentiation property of Fourier transform, we know that if I have a signal whose Fourier transform is given by x of omega, then the Fourier transform of the derivative of the signal is given by j omega times x of omega. We may now apply this property, we may now try to apply this property here. Now we know that the unit impulse is the derivative of u of t. So the Fourier transform of the derivative of u of t must be equals to j omega times the Fourier transform of u of t. You can see that here the Fourier transform of derivative of a signal is nothing but j omega times the Fourier transform of the original signal. Similarly, if we have this Fourier transform of derivative of u of t, that must be equals to j omega times Fourier transform of u of t. Now we know what is this derivative of u of t and its Fourier transform. So this is Fourier transform of derivative of u of t is del t, and this is going to be j omega times Fourier transform of u of t. So this Fourier transform of u of t appears to be equals to 1 pi j omega, because we know the Fourier transform of this del t is 1. So I have simply taken this j omega on the other side, and we have obtained that this Fourier transform of u of t is 1 upon j omega. Now that's what it appears to be. Now let's keep this aside and try to calculate. So let's make this as equation 1 and keep this aside, and let's try to calculate and be convinced that okay, this may be the Fourier transform of u of t, and try to calculate the Fourier transform of a modified version of u of t. Now what I'm doing here is I'm taking the same signal u of t, but I'm shifting the same signal by a certain amount. What I mean to say that is I will take the signal u of t and try to shift this signal a bit. So instead of having this here, I'll try to shift this signal a bit down. So this signal that I'm having it here, let that be shifted by a certain amount, and let me shift this signal by a certain amount, and let that amount be, let's suppose, half. So let this be, I'll delete this, and yeah. Now what I'm doing here is that instead of having this unit impulse, I'm having a shifted version of this instead of having this unit step function, I'm having a shifted version of this unit step function, and the shift that has been incurred here is of amount half. So let's indicate this new function by, say, s of t, this new signal s of t, let that be u of t being shifted by an amount of half. You can see that in previous example, we have considered this u of t where this amplitude was 1 for positive side and that was 0 for the negative side. But here in this case, I have shifted the u of t by an amount of half downwards. So we have the signal that is half on the right and that is minus half on the left. Let us try to calculate the Fourier transform of such signal. Again, this signal does not satisfy Dirichlet condition, but still we are going to prove that this signal also has a Fourier transform. Now we know that this s of t is u of t minus half. If I try to calculate the derivative of the signal s of t, so what I mean to say here is that the derivative, if I look at the derivative of this signal, that is s of t, it is simply derivative of u of t plus minus half. And we know that this derivative of u of t is del t and the derivative of a constant would be 0. So the derivative of this new function, let that be s of t, is del t. And you may be surprised that this derivative of u of t is also del of t, and the derivative of this new function s of t is also del of t. And this is obviously due to the fact that this derivative of a constant is getting 0 here. Now let's try to apply the same property, the differentiation property of the Fourier transform here. So the differentiation property, as we have seen in the previous example, that if I have a signal whose Fourier transform is x of omega, if I have the derivative of that signal, then the Fourier transform would be j omega times the Fourier transform of the original signal. So in this case, that would be the Fourier transform of the derivative of s of t is going to be j omega times the Fourier transform of s of t. Now this turns out to be Fourier transform of derivative of s of t is del t, so that is going to be del t equals to j omega times Fourier transform of s of t. Now this gives the Fourier transform of s of t equals to 1 upon j omega, because this Fourier transform of del of t is 1 again. And if I simply shift this j omega on the other side, we are going to get this equation. Now compare this equation, now this new equation, let that be 2, with the one which we have obtained in the previous example. You can see that the Fourier transform of u of t is 1 upon j omega, that's what we have obtained it here, and the Fourier transform of del of t, the Fourier transform of s of t, the new function that is actually shifted version of u of t, is also 1 upon j omega. The two different signals are having the same Fourier transform. Now that should not happen, because this gives rise to a conflict between the uniqueness of the Fourier transform. If a signal must have a unique Fourier transform. Now after looking at the equations 1 and 2, you can see that both of the signals u of t and s of t are having this, appears to have the same Fourier transform, that is 1 upon j omega. And you may observe that this is due to the fact of this constant being made 0 due to this derivative operation. In fact, you may take any constant. So let this half, it may be any constant. So this signal, if it is shifted by any amount of DC shift or any amount of constant, you are going to get the same equation, that is 1 upon j omega. Now that is the problem. Now which one is correct? Because both of this equation appears to have the same Fourier transform. Let us try to analyze this. Now here in the first part, we have seen that the Fourier transform of a derivative of u of t is j omega times Fourier transform of u of t. Now let us try to take this equation and analyze that equation. So this analysis, what we are doing here is we are trying to compare both of these equations. So I'll make a general comparison here. You can see that here Fourier transform of del t Fourier transform of del t, that is derivative of u of t, is equals to j omega. You can see that j omega times Fourier transform of u of t. This was the equation that we have obtained from the previous example, and the next equation that we are obtained it here is the Fourier transform of del of t is equals to j omega times Fourier transform of this new signal, that is s of t. You can see that from here, this equation. Now just observe these equations because both of these are creating conflicts. Let's consider the case of omega equals to 0. Now what does that mean is, if I take the frequency axis at omega equals to 0, we can see that the Fourier transform of del of t at omega equals to 0 is going to be 0. Let's take another case here. For this case also, when omega is 0, the Fourier transform of del of t is going to be 0. Now let's have a look at the Fourier transform of u of t and Fourier transform of s of t. Now that's what we need to calculate. If we observe the unit step signal, that is u of t, you can just have a close look at this unit step signal u of t. You can see that omega equals to 0 indicates the DC content of this signal, the shift of this signal. You can see that there is some finite amount of DC or the shift present in this signal. The average value of this signal is non-zero. Whereas if we have a look at this signal, that is s of t, you can see that the average value or the DC value here is 0. What I mean to say is that the Fourier transform of u of t at omega equals to 0 may not be 0. Whereas for Fourier transform of s of t at omega equals to 0 will be 0. So what I mean to say here is that when we are trying to multiply this signal by j into omega, that means let's consider this omega factor. When omega is 0, omega equals to 0 in fact removes any component that is present at omega equals to 0. So in order to demonstrate that, let's consider an omega axis. Let's suppose this is the omega axis, that is the frequency axis. If we are multiplying the Fourier transform, so let this be any Fourier transform, let this be the Fourier transform, let that be x of omega. When we are trying to multiply the Fourier transform of any signal with omega, in fact j into omega, what does that mean is, if omega is 0, then whatever may be the Fourier transform of the signal at 0, that is going to be getting annihilated. That means it is going to be 0. But we know that there is some amount of DC, or the average value, present in u of t. The average value of any signal is getting reflected in the Fourier domain at omega equals to 0. What I mean to say is that if this the Fourier transform, that may be any value, that may be any signal, if I have the Fourier transform of u of t, it must have a finite value at omega equals to 0. And just because we are multiplying the Fourier transform by j omega, when omega turns out to be 0, that value that is present at omega equals to 0 will be removed, or that will be made 0. For s of t, the DC content is already 0. The average value of s of t is already 0. Therefore, even if we multiply by omega, when omega turns out to be 0, it's getting multiplied with 0. So that's fine. But it is not fine with this Fourier transform of u of t. So among this appears to be more correct, and it appears to be somewhat fishy. The Fourier transform, this equation, the first equation, appears to be ambiguous, whereas this appears to be more correct. Why? Because the Fourier transform of s of t, that is the new signal here, will have the DC component 0. That means the component that is present at omega equals to 0 will be 0, just because the average value of this signal is 0, and that is getting reflected at omega equals to 0. But for u of t, you can see that for u of t, there is going to be some finite value of the DC signal. That means the Fourier transform of u of t must have some value at omega equals to 0. And just because we are multiplying that with j omega, it is going to be 0. So we are somehow making the value of Fourier transform of u of t at omega equals to 0 as 0. Now, in order to avoid that, in order to prevent the component that is present at omega equals to 0, in order to prevent that component of x of omega, or the Fourier transform of u of t, we take some different approach. So what we are going to do here is that u of t, I'm representing the signal u of t as this signal s of t being shifted by an amount of half. So it's the same thing, this equation, I'm representing it here. So this s of t is, this u of t is s of t plus half, so I have shifted this half on the other side. Now we can apply the linearity property of Fourier transform, and this, if I take the Fourier transform of u of t, then it appears to be Fourier transform of s of t that we have already calculated here. The Fourier transform of s of t is 1 upon j omega, and that we have, that appears to be correct. So we'll be using this equation, that is equation number 2, to give 1 upon j omega. And we know what is the Fourier transform of a constant, that is half. It is simply the constant being multiplied by 2 pi times del omega. So 2 pi, the 2 factor will get cancelled, and we'll have the factor of pi times del of omega. Now this appears to be correct, because there's some value that is present at omega equals to 0. You can see that this value here, if I rub this, I'm having some component that is present at omega equals to 0, and that component is nothing but a a delta function or an impulse. So here I'm going to have this impulse function that is present at omega equals to 0. Something like this. Whose area is pi. Now this function you can see that this function, this element that I'm encircling here was missing. This factor was missing when we were trying to derive the Fourier transform of u of t directly. So this factor, the pi times del omega factor, was missing because we were not considering the factor that is present at omega equals to 0, and that can be obtained by some adjustments by considering the signal that is a shifted version of u of t. This shifted version of u of t is having some special name that is called as a Signum function. In fact, this is a scaled version of Signum function. The Signum function is defined as being 1 on the positive t-axis and being -1 on the negative t-axis. However, we have considered the amplitude to be half and minus half. So this is the scaled version of Signum function, and that Signum function, that is s of t, or that is indicated by as g and the Signum function of t. In fact, it is the scaled version, or the half times Signum of t. Such signal is called as a Signum function. So we have derived the Fourier transform of a unit step signal and the Fourier transform of the Signum function, or the scale version of the Signum function. Now let us try to recapitulate what we have done so far. So let us try to quickly see what we have seen so far. First, we have tried to calculate the Fourier transform of u of t, that is the unit step signal, and we have done that using the property of Fourier transform, the time differentiation property of Fourier transform. And while doing that we obtain the Fourier transform of u of t as 1 upon j omega. Now we have actually tried to calculate the Fourier transform of a shifted version of the unit step signal, that is called as a Signum function, and we obtained the same equation, that is 1 upon j omega. We then analyzed both of these equations here, and it appeared that the equation second appears to be more correct than the first. That means the Fourier transform of a Signum function appears to be 1 upon j omega, but the Fourier transform of unit step needs some correction factor because of this DC content present in that signal. And that's the component that we have derived here, the additional correction factor that is required for u of t is pi times del of omega, and that is due to the fact that this u of t is having some DC, or some average value that is present in the signal. See that the average value of the signal is not 0, whereas for the Signum function it is 0. Therefore, there is no such additional factor that is required in Signum function, whereas it is required in the unit step function. In order to obtain that additional factor, we have analyzed both of this equation at omega equals to 0, and we have applied the linearity property of Fourier transform to obtain this factor, that is pi times del of omega. We shall see more interesting functions, the Fourier transform of some more interesting functions, in the next module. Let's stop here.